So we know they have happened in the past. How can we know that this will happen in the future? This is where we get into a set of experiments which are going on now. The largest publicly funded earth science experiment that has ever been done is EarthScope. And part of EarthScope is that these little green dots here are high precision GPS receivers which have been placed all over the Pacific Northwest. Here's one that's at the airport at Newport. So you guys are familiar with GPS, probably have it in your phones. These GPS, high precision differential GPS meters can determine their location on the surface of the Earth to within an error ellipse which is about the size of a grain of rice. Once you can do that, you can measure not only the motions between tectonic plates on days, weeks, years time scales, but you can actually look at the margin, the North American margin, flexing as it's storing up the energy that's going to get released in the next great Cascadia earthquake. So in our teacher workshops, we go to one of these stations. So this is Teachers on the Leading Edge. These teachers are in our workshop. Summer, August of '09, we're at a Plate Boundary Observatory GPS station at Elma, which is kind of halfway between Olympia and the coast. The GPS receiver is in the background, and they're all pointing in the direction that this station is getting pushed. So here's, we can look now at some of these stations. Take a set of stations that are on the coast here. So look at Neah Bay, Pacific Beach, Tillamook, Newport. Then look at stations which are in the urban corridor, Tumwater, Kelso, Corvallis. And then some stations which are off to the east here, off to the east side of the Cascades. The Juan de Fuca plate is out here, right? It's pushing on this margin of the North American plate. It is actually compressing the North American plate, and we can see that happen in the GPS records. So here's Pacific Beach. So it's getting pushed towards the north, it's getting pushed towards the east. This is 2004 through 2009 here. Figure out the rates. It's about 10.9 millimeters per year to the north, 13 millimeters per year towards the east. Add the vectors, boom. So Pacific Beach is moving about 17.2 millimeters per year, 1.72 centimeters per year towards the northeast. It's being pushed that direction by the Juan de Fuca plate. Take the results from all of those stations and put them together, and what you see is the coastal stations out here are being pushed towards the northeast faster than are the stations that are in the urban corridor. The stations that are on the east side of the Cascades are not moving. So literally, Newport is moving towards Spokane. This whole area, this whole edge, the Pacific Northwest portion of the North American plate is being squeezed like this. So this energy, this elastic energy is building up. We can see it. The boundary is what we refer to as locked and loading, right? It's locked, hasn't had an earthquake for a long time. It's loading it up. It's storing the elastic energy that's going to get released in the next earthquake. If the next earthquake happens tomorrow, Pacific Beach will jump towards the southwest, and it will jump by about 5.35 meters, or 17.5 feet, quickly, right? Sometimes students ask me, when will I know that it's really the big one? And my answer to that is, you will not be in doubt. You will know, for sure. If you are on the coast, if you're in Tillamook when this happens, you'll be on your butt real quick, right? You will not be in doubt. You will know it is the big one. Well, likely sort of consequences of this, there's a whole story about some of the consequences of this and so forth. I'll just point out that this map shows the peak ground accelerations that will be experienced during a magnitude 9 Cascadia subduction zone earthquake. At the location of Portland here, we're on this contour which is labeled 15. That's 15% of the acceleration of gravity. So that means, kind of imagine being shaken back and forth and up and down for about 4 to 6 minutes with a force which is about 15% of gravity. In terms of structures, small houses, wood frame houses will probably do pretty well. They can probably ride that out if the house is attached well to the foundation. Many old houses are not. Problematic. So unreinforced masonry buildings. We have a lot of those in Portland. They're going to be very much stressed by this. They'll have partial or total collapse. Long and tall structures, like long bridges, tall buildings, are particularly vulnerable to this kind of very long period oscillations, like 20-second period oscillations of the Earth that last for 4 to 6 minutes. That can get big, long, and tall structures going that a short earthquake, short duration earthquake cannot oscillate. I think some of the modern high-rise buildings that have been built since the codes have been strengthened, since the building codes have been strengthened, will ride this out okay. They did, right? In Japan, in Tokyo, they rode it out. Some of the older, taller buildings might have significant issues. I'm always asked why we can't predict earthquakes, and my simple answer to that is a demonstration. So, wood, right? Wood, a familiar material. So you all know, here's a wood slat. If I bend this just a little bit, it's elastic, right? So if I bend it a little bit, I can change the shape, bend it, bow it. If I take the forces off, it'll go right back to where it came from. So it's an elastic material. But you also know it's brittle, right? Meaning that if I go too far, if I bend it too much, it will ultimately break. Earthquakes are rocks breaking, right? You're putting forces on them, you build up the forces, you build up to the limit of strength, rock breaks, get an earthquake. Well, you know, if I bend this thing and I just really go for it, you know that this thing is going to break. But the question is, do you know precisely how far I can bend it before it's going to break? I don't know when I do this how far I'm going to be able to bend it before it'll break. Those of you in the first few rows here might have heard some snap, crackles, and pops before it broke. That's analogous to a foreshock, right? It's a few fibers giving way. That sets up the whole rest of the system to fail. If you can't predict a piece of wood being bent to break, right, to its limit of strength, you have no chance to be able to predict when a fault 20 miles or so below the surface of the Earth is going to reach its limit of strength and going to break. You know ultimately it's going to do it, right? It has to. The forces are building up. It will break. But we can't predict earthquakes. We can forecast areas that are going to have earthquakes, but we can't tell when, with any kind of precision, they're going to happen. Well, as far as earthquake preparedness is concerned, that's a whole other talk. But I like the statement of James Roddy, who is the Earth Science Information Officer for the Oregon Department of Geology and Mineral Industries. So his statement is, we are the first generation to understand the geologic hazards that face the Pacific Northwest. We must develop a culture of geologic hazard awareness in the next generation of Pacific Northwest citizens. And in all citizens, in fact, right? But starting in schools is a really good strategy. So this is the group of teachers that we had in our workshop for Teachers on the Leading Edge in the summer of '08. UP people will recognize that this is taken on the steps of Franz Hall. And so what our strategy is basically to teach these teachers about Pacific Northwest geology, earthquakes, tsunamis, volcanic hazards, and so forth. Have them then teach, you know, armies of middle school earth science kids, and just ramp up, you know, the understanding of our geologic hazards in our population. We can build an earthquake resilient society. We can build buildings that can stand up to these earthquakes. We can get smart about tsunami evacuations and what things we do and don't build in tsunami inundation zones. So it's doable, but you got to get on it, and you have to get about the task of personal and societal earthquake hazards reduction. Whether we will or not is a political and an economic question. I think in the wake of this Japanese earthquake, there's a big ramp of interest in this, and I hope that that actually ends up resulting in some serious investment. Slow, steady investment in making an earthquake resilient society is a lot less costly in the long run than paying for all the damage which is produced otherwise. Not to mention the human suffering which is preventable. I'm not saying that even if we do prepare that it won't be a disaster, but there are levels of disaster. So we do know how to do this, and we can do it. Hopefully we'll get about this and we'll stay on it, you know, decade after decade. Hopefully Mother Nature will give us a break, not do it right away because we're not ready, and then allow us, you know, 20, 30, 40 years maybe to prepare for this earthquake that we know is going to happen.